All right, with that, Brandon, go ahead.
Awesome, thank you. There's still a lot of seats out there. People need to get their shoulders comfortable. All right, so what I'm going to be talking about today is the changing server landscape and movement that we've seen over the last few years towards this concept of application operations. I'm Brandon Phillips. I'm the CTO and co-founder of CoreOS. I've been a system software engineer for a long time. I worked at SUSE for a while on the Linux kernel, worked at Rackspace working on large distributed systems, et cetera. And I'll talk about CoreOS at the end, but let's get into it. So open source today powers compute in a lot of ways, and it really is the de facto, as we ended the last talk with, it's the de facto in a number of spots. On mobile, we've become the de facto. On desktop, didn't end how I thought it would end when I was working at SUSE, but we have sort of taken over, open source has taken over on the front end of the web. It wasn't really the Linux desktop that ended up winning, but it was the front end web where most applications live today. Server infrastructure, virtualization in Linux, raw compute infrastructure, web backends, our web servers or languages, databases, data processing. All these things sort of have become the de facto best in breed sort of technologies for the vertical that they're in. And they're all open source. The one area that I think we've kind of had this mystique around over the last probably decade is Google's infrastructure. It's always had mysterious names like Borg. There's been white papers that kind of come out every few years. And it's been this thing that people have had respect for, they've had interest in, but we really haven't had a solid set of technologies and tools that we take off the shelf, like these other open source components, and use to get Google-like infrastructure. And when I say Google's infrastructure, it could be Twitter's infrastructure, Facebook's infrastructure, but it's this infrastructure that we respect because it's these large global internet brands that run these huge amounts of infrastructure and data centers. And so what this talk is about is how the industry, how us as open source communities are building this Google-like infrastructure for everyone else. It's been called cloud native, but I really like this Google-like infrastructure for everyone else because it has this great little acronym, GIFY, or Jiffy, depending on how you like to pronounce things. It starts with G-I-F. And it's ultimately hashtagable, which is great. This is really important in the modern age. So I'm going to use the term Giphy, and what I mean is Google infrastructure for everyone else. All right. So what makes Giphy compelling? So Google wrote this paper, one of the many papers describing how the infrastructure works, called The Data Center as a Computer. But really, if you get down into it, it explains sort of operations paradise. Okay? It explains this world that a lot of us have tried to achieve. Many of us have the scars and paper cuts to show that we've tried to achieve this. But it's a world where if I add more hosts to my infrastructure, my applications get more scale. I'm a software engineer, so I need to make a small correction to this slide. I'm also a JavaScript engineer, so I need to make one more correction to this slide. And so traditionally, the way we thought about infrastructure is we've thought about it as racks and racks of compute. This is what we pay our infrastructure as a service providers. This is what we make our CapEx against when we buy hardware. It's, my application has some needs. I'm going to go off and buy some hardware to fulfill those needs. And I think about it in RAM, I think about it in CPU, and then I think about it in the operating system that I install on that. Now, this Google-like infrastructure has a different point of view, a different perspective. It talks about, I have a copy of my application, and this is going to be the iconography that I use to this talk is going to be this little cylinder, but this is a copy of our application. And it has some inputs. It says I need 2,000 milli-CPUs, and I need 2 gigabytes of RAM in order to operate. Those are the inputs to the system. The outputs is that this application is going to be able to handle 1,000 requests per second, given these inputs. Okay? So we start to think about not how fast is my CPU, how much RAM do my servers have, what does my application need in order to fill X number of actual user requests? So we move from this to thinking about this, where I think about metrics of my application and whether it's healthy or not, how many requests it's able to handle at this moment. And then I get into this world where I'm able to add another server, another copy of the application, and I get more scale. The next property of this whole system is the idea that if an individual host fails, everything's going to be okay. This is something that a lot of us would love to say, right? How many people would really appreciate it if I walked into one of your data centers and unplugged things? Would you be happy with that? Would you get a page? Would that be a bad day for you? Would you probably give the intern a stern talking to if he spilled coffee on one of your racks? So these are things that we concern ourselves with, but a lot of us spend a lot of time and energy trying to get there. And so this whole idea that if I lose a server, I lose capacity, but my application remains healthy. And the other part of this operations paradise is that I'm able to do really trivial, easy application rolling updates with rollback. It's really important if you're going to update something that you plan for failure, because all of us are non-perfect. There may be a couple of you in here that are absolutely perfect, but most of us make mistakes, and you need to be able to undo those mistakes. And so this idea that I have my servers, I have them all running the green version of the application, I roll out the red version, things start to go bad, I start locking the database, something's going terribly wrong, able to roll that back, figure out what happened, fix the bug, and roll forward and update the application. And this is an operation that happens multiple times a day on a scale of minutes and hours, something that's just a normal part of the healthy operation of my infrastructure. And then the last bit is efficient utilization of servers. I always like to tell this thing that my wife worked really hard as an engineer on hydroelectric dams in Oregon. And I always felt terrible working in infrastructure software, because you'd log into production host and you see 3% utilization, 4% utilization. My wife is out there rappelling down inside of dams underwater in order to generate all this energy. And then what are we doing with it as technologists? We're kind of just burning it off the back of the CPU and just wasting all that energy and effort. And so this is about, I have my application is running across my hosts, but a lot of times the applications are sitting there bored. I want to be able to launch and manage lots of other applications on top of those servers. And then on the other side, it's not just about operations. It's about this idea of the application engineer, the application operations, needing very, very consistent infrastructure, consistent operating systems, consistent places to deploy, really trivial scaling, so that when they get additional demand on their application, say their load balancer says they're getting 7,000 requests per second, the app says that I'm able to handle 8,000, they're able to make those really trivial scaling decisions and be able to roll these applications out in an easy way. So how do we build this, right? How do we get to this operations paradise? Well, we need to build a lot of new open source tooling, which is exciting and fun. It's also going to be, we're going to be tearing down a lot of the software and infrastructure that we've built in the past. It's going to be scary. People are going to say, why are we doing this? So let's talk about these new layers that we kind of define with this infrastructure. So we'll tell some stories. Let's start with you as a software engineer. So as a software engineer, your role in this new way of building infrastructure is that you take your source code, really sophisticated stuff, doing hello world in a variety of languages, and you build that into a container image. And these tools for building the container image, you can use our existing tools like Jenkins, new things like Docker files, et cetera. It doesn't really matter. It's about transforming your source code through compilation or whatever into a container image. And these container images aren't anything mysterious. They're generally a tarball that includes everything that you need outside of a kernel, inside of a tarball. So if you're a Java app, this is your JVM and your jar, your bytecode. If it's a Python app, it's going to do the Python runtime and your actual just Python script. And so this is really what a container image is. It's just your compiled source code, if necessary, and the language runtimes devoid of any thing like a kernel. And then you package this up. You package it up and give it a name, because human beings are way better at names than remembering hashes. I'll challenge you at the end of this talk to read me back that cryptographic hash of this container. We'll see how many of you get it right. And so you want to give it a name so that you can type that into configuration, monitor it, etc. And hopefully, we get into a world where we start to sign these things, because we want to be able to say, I only trust a subset of my developers to deploy code. And so if Alice wrote the code, I want to make sure that Alice actually certified with her public key that I'm going to deploy this to the hardware, or deploy this to the infrastructure, and the infrastructure trusts Alice because she's a known developer. So the motivation for all this container stuff is that I no longer have host dependencies. I no longer am depending on the Python and the Java, et cetera, running on the host. And that's what's kind of now the responsibility of the application engineer, is to package things up so there's no host dependencies. And the nice thing is that this means that I can run lots of different things on top of a single host, and those things don't conflict. They're just consuming resources. Now, we get into this world where we have a lot of different types of operations. We have the OS operations, cluster operations, and application operations. So as an OS operator, what are your responsibilities now in this new way of building infrastructure? Your responsibilities actually get easier because our applications don't have these host dependencies. We're able to move from this world where we used to have these flag day of operating system updates, where we move from one version to the next, kind of a painful situation. But now, with less host dependencies for the application, we're able to actually experiment and do regular rolling upgrades of our servers. And we move out of this world where we are afraid of updating. And just slowly making this progression of updates all the time. As cluster operations, this is kind of a new role. This is where we're actually providing an abstraction. We're providing an API across a lot of hosts, where you're able to talk to that API, and no matter whether there's 1, 2, 3, 1,000 hosts, there's a consistent API whereby you say, I need to deploy this app, and I need to run some copies of it. And then your job as an application operator is you say, whatever amount of compute that's out there, I have this application that I have, column example web app, and I want 3 copies running to be able to handle my load. So this is kind of these new kind of divisions of responsibility that are enabled. And what it enables overall is a separation of concerns, where OS operations is in charge of getting up the container runtime. Cluster operations is about creating a nice dependable layer for getting work down to the machines. And application operation focuses on the health and capacity of the application itself. And we get into this world where the underlying infrastructure, the underlying operating system, the container runtimes kind of matter less if we do this right. And what's really important is just making sure that application is supported and has the infrastructure it needs to run. So what is CoreOS? So CoreOS is a container-focused Linux operating system, most of all, open source one. You can find it at CoreOS.com. Kind of the namesake of the company is CoreOS. But we're also a number of open source projects that's supporting this new Giphy, this new style of running infrastructure, etcd, a key value store, Flannel, a networking system, and Rocket, a container runtime. These are open source communities and projects that we've started and foster at CoreOS. And so if you're interested in this sort of new wave of infrastructure, we would appreciate you joining our communities. There's a bunch of interesting stuff going on besides these projects at github.com/CoreOS. And we also build products that enable Giphy. We have things that build containers and host them, et cetera. We have a full stack of stuff that enables this type of technology. And so what we're really doing is we're building these layers, building the software to build this sort of infrastructure. CoreOS Linux, helping out in building container runtimes, and then building these cluster operations tools. If you're interested in this technology or you'd like to see a demo, I have a more technical deep dive at 2:30 on the DevOps track. All right, thank you so much.